Students, friends of BSc second sem, we have completed kinetic theory of gases topic, and as I assured, we will solve some numerical problems on this. Before that, you students, friends, dear students, please listen to me that University has announced the mode of examination for this semester, that is odd as well as even semester. They are conducting the pending examination as well as the even semester examination, and the examination mode will be multiple choice questions. So normally your paper is of 80 marks theory, either it is first sem or second sem. For 80 marks, they will set 40 questions, each carries 2 marks, and multiple choice questions. One correct answer will fetch you 2 marks. So, to prepare in this direction, that is multiple choice questions, I appeal to the students that whatever the portion or the portion to be covered, student has to read in detail. They need not prepare the descriptive answers. In turn, they should themselves can frame a question and find the answer, that is multiple choice, or else they can refer to different books and go through the multiple choice questions and their respective answers. Will also support in this direction, will also guide in this direction. I will set some of the questions on my portion and I will discuss with you. So here in 40 questions, some of them will be numerical problems. That means the problem will be stated in the form of a question and its answer, one of the answer will be correct, 4 alternative answers will be given. Student has to work out, solve it in a rough page and select or choose a correct answer. In that direction it will help us. So I will summarize here the important formulas or formulas in kinetic theory of gases. Formulas in kinetic theory, KT, kinetic theory of gases. Fine. So the first one is the average velocity, C average. This can be written as V bar also, or it can be written as C average. Fine. So this C bar is given by this 2 upon square root of pi B. B is constant, and the constant B is m upon 2 kT. A is also constant. A. Velocity distribution law. A and B are the constants. This A is given by this B by pi, and the square root this is, or A is equal to, and the square root m upon 2 pi kT. T is absolute temperature, K is gas constant, means Boltzmann constant, m is the mass here. So this is one relation. The second relation or the second formula, CRMS, root mean square velocity, that is equal to square root of C bar square, that is given by this. Say it is 3kt by m, small m, or this can be written in terms of RT and the square root, that is 3RT upon capital M, where M is equal to capital M is equal to N, the Avogadro number, into mass, called as molecular weight of a gas. R is equal to N into K, where N is Avogadro number, K the Boltzmann constant. Most probable velocity, CMPV, most probable velocity, that is under square root 1 by PV, and this is equal to 2 KT upon M, that is under square root 2 RT upon capital M. So this is, so the ratio of this, that is C bar, C average, RMS, and most probable velocity, say CMPV, same as this, C bar, same as say CRMS, is equal to say 1. If it is 1, then this will be equal to 2 upon root pi, that is equal to root 3 by 2. So this can be written, this is equal to, say here it is this, same as 1 is to 1.28 is to 1.225. So these are the certain formulas. So mean free path, I'll write here, mean free path lambda, that is given by Clausius expression, lambda 1 upon pi d square n, where d is the diameter, where d is diameter, and this is Clausius expression for lambda, that is mean free path. So Maxwell's expression for lambda, Maxwell's expression for lambda, that is equal to 1 divided by root 2 pi d square n, where d is the diameter. Let's go for the transport phenomena. Say transport phenomena, that is coefficient of viscosity. Expression for coefficient of, these expressions, these formulas will help us in, say, solving numerical problems, simple problems as you have faced in CET. Coefficient of viscosity. that is eta is equal to 1/3 rho v, say, that is average velocity into lambda. Lambda the mean free path, v the average velocity, rho is the density. Instead of this you can write even c, where v bar or c bar average velocity. This we have derived in detail, we have discussed this. Let us go for thermal conductivity. Thermal conductivity denoted by letter K. Thermal conductivity based on conductivity K is equal to 1/3, say, rho c average velocity, specific heat at constant volume, and lambda the mean free path. So using this lambda I can write this relation, that is 1/3 root 2 m c small c c v upon pi d square. This is what using for lambda here. The relation between these two, that is coefficient of viscosity and thermal conductivity, relation between K and eta. K by eta is equal to C into V. This is coefficient of viscosity. Coefficient of viscosity and the thermal conductivity is this relation. Coefficient of diffusion. Coefficient of diffusion D is equal to 1/3 lambda into C, that is C average. Now the coefficient of diffusion and, say, coefficient of viscosity. So D is the coefficient of diffusion, eta is the coefficient of viscosity, by rho the density. These are certain relations. Let us take simple problem of worth 2 marks. I'll write it here on the board. Problem number 1. Determine the RMS velocity. Determine the RMS velocity of argon gas, GON gas, at 27 degrees centigrade temperature is given. At what temperature will RMS, at what temperature will RMS, say, root mean square velocity, RMS velocity be double at this temperature. Okay, let us see. Given atomic weight of argon is 40. This is given. We know that CRMS, only this will be given and the 4 answers will be given. It had to solve it in short. So that is 3RT upon capital M. The clue for solving multiple choice question, as you have experienced writing CET level questions may be bit tougher. Here questions will be bit easier one. Hope so. It depends upon the question paper setter here. So this is the formula. M is given, that is 40 grams per mole. That we can convert it into kg, that is 40 into 10 raised to minus 3 kg per mole. Temperature small t is given, that is 27 degrees centigrade. Capital T will be small t plus 273, and this will be 300 Kelvin. It is in Kelvin. R, the gas constant, you must be knowing this, then we are not giving. R is equal to 8.31 Joule per Kelvin per mole. So let us substitute for R, T and M. So when you substitute in this CRMS, okay, substitute this, that is 3 into 8.31, that is R into 300 divided by 40 into 10 raised to minus 3. And when you simplify this will be in meter per second, that is 432 meter per second. Just to work out if there is a, and this velocity will be double at temperature. At what temperature it will be double? That is what he has given. So temperature. Okay, let me rub this. I'll keep this for 432. RMS velocity, I'll write in short, will be double. This is one data, double at temperature, some other temperature, that is T1. I'll take this. So this will be equal to CRMS. Again the same relation, 3RT1 upon M. This will be double, that is, say here 2RMS, CRMS is equal to 2 into this, that is 3RT upon RT1 upon capital M. So if you simplify this, that is 2 into RMS is this, square root of 3RT upon M. So this is 3RT1 upon this, say here 3RT1 is equal to 2 times square root of 3RT upon M. So square root of T1 is equal to 2 times square root of T. T we have calculated, T is equal to 400 and that is T is equal to 300. Kelvin. So this will be T1 will be equal to 4 times T. This, if you reach to this orally through the practice, you will get it. Your answer T1 is equal to 4 into 300. It will be 1200 Kelvin. This type of simple problems you have to solve in the examination. Hope so. And these problems will not be too many. Depending upon the weightage on each topic, they will be framed. You work out this. I will write at what temperature RMS speed of molecule of hydrogen will be equal to nitrogen molecule at 35 degree centigrade. This is so atomic weight of nitrogen is given, that is equal to 40. Similarly, you have to work out this. Let me go for another problem here. That is the RMS speed of hydrogen. The third problem, the RMS speed of hydrogen molecule, better you write molecule, at NTP, normal temperature and pressure, is 1.84 say kilometer per second. It is kilometer. Determine RMS speed of oxygen molecule at NTP. This is CRMS square root of 3RT upon M. Okay, so here the CRMS of oxygen to the CRMS of hydrogen will be equal to under square root NH upon MO, that is oxygen. So here it is hydrogen, it is molecular weight is 2, and for oxygen it is 32. This will be 1 divided by 16, this will be 1 by 4. So RMS of oxygen that is equal to 1 by 4 CRMS of hydrogen. That is 1 by 4 into 1.84, that is equal to 0.46 kilometer per second. So let us go for one more. Pressure remaining constant. Say pressure remaining constant. Calculate temperature at which RMS velocity of the gas will be half of its value at 0 degree centigrade. So this will be T1 is given 0 degrees solution, you can say that is plus 273, that is 273 Kelvin. It is conversion. T2 we have to calculate this. So simple here, CRMS is equal to half the CRMS 1 is equal to half the CRMS 2. Okay, so this will be equal to, I'll write this formula, that is in terms of KT, say 3 KT, say T2 upon M is equal to half under square root 3 KT 1 upon M. So square root of T2, this gets cancelled, okay, is equal to half, here it is, half square root of T1, or T1 is equal to T2. If you square it and finding this, T2 will be equal to 1/4 because it is squaring into 273. This will be, say, 68.25 Kelvin. So you have to go for this. You need not, only thing you should know the concept properly. That's the key here. Let's go for simple relation. If the coefficient of viscosity of nitrogen, if the coefficient of viscosity of nitrogen if the coefficient of viscosity of nitrogen is, so it is given 1.66 into 10 raised to minus 5 SI unit. He mentions it as SI unit, and the molecular specific heat, and the molecular specific heat at constant 6 calories Calculate the coefficient of thermal conductivity. Calculate coefficient of thermal conductivity. Thermal conductivity. Here this problem is simple and it is 2 marks work. While framing them is what is the coefficient of thermal conductivity. So it is given, it can be simplified. N2 eta is given, that is 1.66 into 10 raised to minus 5 SI unit, SIU. CV, they may give this, say it is given in calories, 6 calories. It may be converted into joules per kg per Kelvin. So this is CV, specific heat per gram. Okay, those 6, that is a molecular weight 6 by 28 calories per gram. This is, so if you convert this into kg, CV is equal to 6 into, there is a conversion factor 4.18 divided by 28, it should write kgs. 3, this will be say 8.595 joules per, say joules per kg per Kelvin. This 8.95. Here instead of this, if they give this, the problem will be still simpler. We know this K upon eta is equal to C into B. So what they want is K is equal to eta into CV. Students, friends, please work out. Don't sit idly, work out on this, in this direction. If you substitute eta and V, say K will be equal to 14.88 into 10 raised to minus 3 joule per meter per second per Kelvin. Thermal conductivity. So similar type of problem you can solve on this. Let us go for a problem on